Everyone, so we're looking at charge on conductors here. Like we saw in class, we did the demonstration where we put charge all over a metal sphere and we asked where was the charge sitting, and through the demonstration we were able to show that all charges, since they are the same sign and the surface was a conductor, will repel each other to the outside of the conductor at all times. We can prove that with Gauss's law. So if I have a shell here that has positive charge on it, if I make a Gaussian surface inside, I can see that I've enclosed no charge. So according to Gauss's law, E dot dA says that there's no charge enclosed, then there must be no electric field there. So if there's no field inside the shell, then the charges aren't going to feel any forces. So if our Gaussian surface encompasses the entire shape now, we now do have a charge enclosed. We do not eliminate the right side of Gauss's law. We leave it as Q over epsilon 0. Remember, the field is uniform at all locations a distance r away. So when we do that, we end up getting Q over 4 pi r squared epsilon 0, which is the formula for point charge. There are no charges on the inside of a metal, they're all on the outside due to their mutual repulsion. We did examples with the Van de Graaff generator in which of the pi pans would fly off. I'll leave a link here for the video where I got that idea from, and for the idea of a Faraday cage, like we talked about with what is the best suit to wear in a thunderstorm. You can look through those videos if you still need more convincing that all charges on conductors are on the outside of the material. So when we do that, we can say that, well, if we have a shell and the shell maybe is neutral and we put a charge inside the shell, the charge will induce charges to separate from the shell. So if you put a positive in the middle there, negatives will come to the inner surface, positives will repel to the outer surface, and create two surfaces for you when we do that. Alright, so let's start with an easy example. We'll say that this shell is neutral. So net charge equals 0. And we'll put a plus 2 charge inside that shell. That means it's going to create an electric field that goes away from it in all directions. And since the shell is neutral, it doesn't mean it has no charge, it has no net charge, which means that negatives are going to see that positive in the middle and drift towards it. And because the outer shell has lost its electrons, the outer shell now becomes positively charged. Now if you want to know what numbers to give each of the parts of your shell, the inner and the outer surface, it depends on what we initially had the shell charged at. Since it was charged at 0, that means negative 2 went to go towards the middle here, so we have a negative 2 charge on the inner shell, and to make the entire shell neutral, this has to be a positive 2Q out here. If you remove that inner charge from the scenario, the negative 2 and the positive 2 will go back together and become neutral in the end. So based on your charge distributions, you can see how the charges want to move around due to induction, or you could think of it like polarization, but polarization is more for insulating materials, not conductive materials. So it doesn't even matter if I have the charge at a different location inside the shell, it's still going to induce those negatives just like it would if it was at the center, and repel those positives like it would if it was at the center. So the shell itself is neutrally charged, has no net charge, and if you are inside the metal, if you're inside the walls of that charged shell, you feel no electric force. Now, in the homework, they're going to give you different setups for the solid sphere in the middle versus the shell that is charged, either positive, negative, or neutral. So let me do a couple examples like that. Alright, so here's our example. We got a plus 5 charge in the center, surrounded by a shell that's already charged positive 8. Meaning that that shell is missing 8 electrons. Well, if we want to know the charges on the inner and outer surfaces, we need to know that since there's a positive 5 in the middle, 5 electrons are going to come towards the middle and try and meet that positive 5. So the inner shell becomes negatively 5 charged. And if we look at the outer surface now, the outer surface was a plus 8. But 5 more electrons have now moved to the inner surface. And if 5 more electrons move to the inner surface, the outer surface that is positive must now be at a plus 13. And how did I get plus 13? Because my plus 13 and my minus 5 give me my net charge, which is plus 8. So the total charge of the shell must still remain the same, even though the charges have shifted and induced and separated. Now, a thing that they like to do is say, okay, we've got this set up because of that charge being present. Let's say you attach a grounding wire to the outer shell. And if we attach a grounding wire, what you could say is that those 13 drain to the ground and the outer shell becomes 0. Remember, electrons are the mobile things, so really electrons are going to come from the Earth and they're going to see that plus 13 and they're going to completely neutralize the plus 13 on the outer shell. So we're going to lose every single positive on the outer shell here due to those electrons coming from the ground. And when that happens, they then say disconnect the grounding wire. So the grounding wire goes away. Now let's eliminate that charge from the middle. So they pull out the positive 5 that's in the middle, and you're left with the negative 5 on the inner shell. But the negative 5 is not going to hang out on the inner shell. Since they're all electrons, they're going to repel each other. And so all negative 5 will now move from the inner circle to the outer circle, leaving a negative 5Q out here. They come up with these scenarios to see if you can understand how charges are going to distribute themselves and move around in different scenarios. We've got a +1 and a -9 net charge. Again, that outer shell is going to sense that there's a positive inside and send a -1Q on the inside to meet it. Well, if the outside had 9 extra electrons and one of them left, we're left with now, on the outer shell, still negatively charged, but charged at -8Q. Because if you look at the inner and outer surfaces, the total adds up to -9. Again, attach a grounding wire, and those electrons are going to see that there is a better location that they can go. Those 8 electrons are going to run down to Earth. Means that I eliminate all my charge on the outer shell, detach the grounding wire, and remove the inner charge. Removing the inner charge takes that -1 charge on the inner surface of the shell and puts it to the outside. So you're able to induce charges to separate and shift them around just because of their nature, of the positives attracting negatives and vice versa. If we hadn't attached a grounding wire and we left our setup like this, what you could do is graph the electric field strength with distance. We'll call that inner radius A, we'll call the outer radius here B, and we can make our distance whatever distance we want. So if I graph electric field strength here versus our distance, what we can do is see how the electric field strength changes. Well, if we take our first Gaussian sphere and surround that inner charge, well, that inner charge is positive. I have Q enclosed. It's a point charge surrounded by a Gaussian sphere. So from the point charge out to radius A, I'm going to see my electric field strength die off to location A. Once I get to in between A and B. In between A and B, I'll make my Gaussian surface right here. And if I look at my total Gaussian surface, I do have charge enclosed. However, I've enclosed a positive and a negative. So my net charge is 0, which according to Gauss's law, with a net charge of 0, there's no net flux, which means there's no electric field. And I'm inside a metal. Of course there's no electric field inside a metal. So my electric field strength would drop off to 0. All the way until I get to location B, when I get to the outer radius. When I get to the outer radius, I make a Gaussian sphere out here. And the Gaussian sphere out here does include some charge. It includes the +1, the -1, and the -8. So really, I see that there's a -8 net point charge that's going to die off as KQ over R squared all the way out here. So this is at the radius of A, this is at the radius of B, and beyond. What you're seeing there is that the graph does not form a continuous line. This is a discontinuous graph. And discontinuity is really just showing that any charge distribution that you cannot graph on a continuous curve, we call discontinuous. So like the plane of charge here. The plane of charge had electric field to the right or to the left, but if you were inside that plane of charge, you would have no electric field strength. So you can't draw a continuous line from one to the next. Or like we just drew, the electric field was from the point charge in the middle to the inner shell. There was electric field, so we had a strength. But as soon as you got inside the metal, the graph dropped to 0 because there's no electric field inside. And then it dropped off again as we move further and further away. Here's a visual of two charged objects with some conductive strips. You can see that the conductive plate here is positive or negative. The ring itself is electrically charged, positive or negative. They must be oppositely charged here because you can see that there is field moving from the circle to the slab or vice versa, depending on what the signs are. But if you look at the middle, in the middle of that picture, you don't see any of the little pieces of thread reacting to the electric field. So that means that inside those metals, you are perfectly electrically shielded. There is no electric field strength inside. So from this example here, you can see that we've got this potato shape of charge, and they made a flat disk there of area for our Gaussian surface. We know that at point P here, the electric field points away in both directions. It points out from the top of the potato shape and inward from the other side of the potato shape. Since there are two sides to the electric field, because this other surface has electric field pointing in and out, since we can see them as two planes, what you get over here is two electric fields. You get electric field from one plane and you get electric field from the second plane. And when you add those, since it's sigma over 2 epsilon 0, adding basically sigma over epsilon 0 divided by 2 twice, you just get sigma epsilon 0 for the total electric field strength pointing away from this charged potato. Again, inside you'd have no electric field strength whatsoever, but outside you'd have a strong field away in both directions. So you can see our Gaussian surface here. Inside the potato is 0. There is no charge enclosed, so you get no electric field in that odd shape, but you do get electric field off in all other directions. Hopefully this will help you solve some of the odd shapes that you had and distributions of charges in your homework.